So our second skill here in our first learning unit on intermolecular forces, thinking about phase changes, has to do with thinking about vapor pressure and what vapor pressure is, and then phase diagrams. All right, so let's first define what vapor pressure is. So I want you to think back to when we had Unit 5 in Gen Chem 1 on gases, and we talked about partial pressure of gases. Partial pressure was a way of sort of measuring the concentration of gas that we'd have, or molecules in a gas phase. You can think about vapor pressure sort of being the same thing. We're going to think about the amount of gas that we have in solution. So conceptually, I want you to think about that. Envision this for a moment. When we put a liquid in a closed container, we're going to have molecules that evaporate, right? Just think about if you had a bottle of water, right? You're constantly going to have some molecules that are escaping the liquid phase and existing in the gas phase, but you're also going to simultaneously have some gas molecules that go back from the gas phase into the liquid phase. And they're going to kind of undergo this back and forth process until what we have is the vapor pressure is reached. And again, we can think about that as representing the concentration of gas that's going to live in that gaseous space. So going back to our bottle analogy, if we took the cap off of that bottle, we'd continue to have gas molecules that would escape and more liquid would go into the gas phase until eventually we evaporated all of our water. But if we keep that cap on, we're going to reach a certain amount, let's call it a steady state amount, that reaches a certain pressure of gas that's in there, a certain concentration of water molecules that would be in the gas phase. This back and forth, this concept of what I just called a steady state, is going to become an important concept in a few units from now. We're going to refer to this as a dynamic equilibrium. Okay, that means no more changes are necessarily happening. It's not saying that these processes aren't happening. We're still having evaporation and condensation, but they're happening at the same rate. Okay, and that means the net change is not happening. We're going to have the same number of gas molecules in the gas phase. That vapor pressure is going to be the same, right? And we highlighted this is like when you learned about partial pressures, right? That's the amount of gas at a given temperature that's in the gas phase. We define that as vapor pressure. Okay, so vapor pressure is going to be something that we're going to see as a thread through a few more units. So I wanted to make sure to review that. You've actually seen this before. Do you remember the lab that you did in Gen Chem 1 where you actually had to collect the gas over water, right? And so you had this gas that you collected over water, and then you had to subtract out the concentration or the pressure of water vapor that was there. All kinds of things that we had to do that are kind of concepts of this same aspect of vapor pressure. All right, so conceptually, I want you to think about what it really means to boil something. Okay, I want you to think about boiling as really a temperature-dependent evaporation. Right? Because boiling is really just taking something from the liquid phase and moving it to the gas phase. So by having a substance that we add heat to, we help that process along. But really what's happening is we're having a battle between molecules that are in the liquid phase wanting to escape to the gas phase, but we've got atmospheric pressure that's pushing down. And what happens is we heat up a substance is we provide those molecules with more energy such that they can overcome that compensating force, that external pressure. So again, this battle happens between molecules acquiring enough energy via heat to break free from their neighbors and go from the liquid to the gas phase, and then atmospheric pressure pushing back to keep them in their liquid phase. So we've got this balance. And the more heat that we add, the more that we're going to be able to overcome that external pressure and allow all of those molecules to escape. So we can define and say that a substance boils when molecules in the liquid phase acquire enough energy to break free from atmospheric pressure. Now, this is a really important piece because it tells us that there's a pressure dependence to temperature. So I've got an extra credit question for you. Little kind of Easter egg put in here. You need to send me an email and let me know the answer to this. Is the boiling point for water always 100 degrees C? And you can't just answer yes or no. You have to explain your answer. And I've got a couple of hints here. This is a pressure cooker. And here's some directions about high altitude cooking. So think about that. Send me an email and you can get some extra credit. All right. So let's define what we mean by a boiling point and introduce this concept of a normal boiling point. We can define boiling point again as the temperature at which vapor pressure equals and thus overcomes external pressure. We've given molecules enough energy that they can live in the gas phase and overcome that atmospheric pressure. Okay? We define normal boiling point as the boiling point at 1 atmosphere or 760 torr. Another plot here to take a look at. Here we're looking at plotting the vapor pressure as a function of temperature, right? So here's atmospheric pressure, and let's see where we intersect these lines. Let's take water, which we know. We intersect this line at 100 degrees. That makes sense, right? If we're at atmospheric pressure, water is going to boil at where I intersect this blue line, 100 degrees. Now take a look at this. If I live someplace to the left of this line, I'm not boiling yet. If I live to the right of this line, I am boiling. So let's see what this means. If I am at atmospheric pressure, but I'm over here, I'm at 90 degrees. Well, I know that water doesn't boil at 90 degrees. I'm to the left of this line. This is interesting. It looks like water might be able to have a boiling point greater than 100 or less than 100. I'll give you a hint. That will help you answer the extra credit question on the previous page there. But you will have some questions potentially on your online quiz that deal with thinking about this plot. So the big key is if you live to the left of the line, you're not boiling yet. If you live to the right of the line, you are boiling. Okay? And so we've got 3 different substances that we're evaluating here. All right, last part to this. There is a quantitative piece to this skill, and it looks scary, but don't be scared, okay? Here's an equation that we're going to use. Now, I want to just give you a little bit of a heads up of how we got there. We just talked about this plot. This plot looks at vapor pressure as a function of temperature, okay? Now, one of the things that scientists love to do is plot things in a different way so we can get them to be a straight line. So when we plot not vapor pressure, but the natural log of that, and not temperature, but 1 over temperature, we can get straight lines. And the beauty of straight lines is we can get y-intercept and slope information that can give us important things. You don't need to remember that, but this essentially is the equation of a straight line that has a whole bunch of variables in it. Don't worry about it. Do you remember when we had the changing variable type problems with our gas law from Gen Chem 1? And we had all of these different variables. And we said, don't worry about it. You're only going to be solving for one. You just have to keep track of everything. The same is true here. We're going to have, and it looks like there's 6 different pieces of information. We've got 2 different pressures, 2 different temperatures. This is a constant. R is a constant, okay? But this is usually a piece of information we're interested in. The delta H, the enthalpy of vaporization, that's a constant for a substance. So again, you might have problems where you want to solve for this important property, or maybe you know what that property is and you want to solve for a new pressure or a new temperature. Okay, so you might have a problem that you're going to see like this. Well, you will on your online quiz, that you're going to have to know how to use this equation and solve for an unknown. We'll do some problems in class that deal with that. The last little piece from this is a qualitative piece that has to do with understanding how to interpret and think about what we call a phase diagram. So a phase diagram, again, another plot, it looks at plotting the pressure as a function of temperature, okay? And what we can see here is there's 3 different colors here. We've got solid, liquid, and gas. And you can always remember which is which because we always go from solid to liquid to gas as we go from left to right, increasing temperature. So whatever kind of section is furthest to the left is our solid, and then we're going to start seeing liquids, and then gases are all the way to the right. So that'll help you identify which phase is which. Now we can see that we've got lines here that separate these colors. These represent phase changes. So this again between solid and liquid, that's where melting and freezing happens. Going between liquid and gas, this is where vaporization and condensation happens. So you want to make sure you know those terms. Two new terms that might be a little bit less familiar to you are going from solid to gas or gas back to solid. These terms are called sublimation or deposition. So two new vocab terms you want to make sure you know. So phase diagrams, again, tell us what the state of a substance is at a given pressure, which we measure and look at on our y-axis, and temperature. Okay? Don't worry too much about, there's things called a triple point or a critical point. Don't worry about those, but this is kind of an interesting thing. Did you know that there is a temperature and a pressure where you can have all three phases existing simultaneously? Think about this from a water standpoint. That means there's a pressure and a temperature where I could have ice, I could have water vapor, and I could have liquid water all existing at the same time. I've got water that's freezing, melting, and boiling all in the same spot. Okay? Unique temperature and pressure will create this triple point. All right, so these phase diagrams, again, the anatomy is such that if we draw a horizontal line, if I draw a horizontal line here, that means I'm keeping pressure constant. So if I keep pressure constant, so we have a given pressure, molecules can assume any of one of three states depending on the temperature, right? Think about a practical example for this with water, right? If I'm looking at 1 atmosphere, which is 760 torr, I can either be a solid, I can be ice, and then at 0 degrees, I'll transition to a liquid, and then at 100 degrees, I'll transition to a gas. So think about practical examples that can help make sense out of this. Let's draw a vertical line, right? If I draw a vertical line here, that means I'm holding temperature constant, okay? If I hold temperature constant, that means I can go through one of three states depending on the pressure that I'm in. So think about a practical example of this with the propane tank that you use for your barbecue grill, right? I can be a solid, liquid, or a gas at room temperature depending on the pressure, right? So if I keep my temperature the same, I'm at room temperature, I can have, if I really increase the pressure, I actually could make propane be a solid, but that's really hard to do. But practically, you can pick up your propane tank. You can feel, it feels like liquid sloshing around inside, and that's because it's under high pressure and you've made that propane gas be a liquid. And then once it gets out under atmospheric conditions and that lowered pressure, it becomes a gas. Okay, so some practical examples to think about. So what do you need to do with a phase diagram? It's all going to be qualitative. You're going to see some questions where it's asking you maybe what's the name of this transition that's going on? What's a likely temperature for a melting point, right? So you're going to need to know, without all of the information here, where solids, liquids, and gases would live, kind of what these different lines represent, and it's all qualitative pieces of information. All right, so that's vapor pressure and phase diagrams.